This problem can be a little bit tricky if you don't have a framework to follow going into it, but I'm going to show you all of the tricks that you're going to need to solve it. And once you do it for that first time, you'll be able to do the second and the third one pretty easily. So it starts out pretty simply. We're just going to take our Hg ion and our NH3 and write out an expression that shows the formation of this complex here. So I have Hg2 plus my NH3, and I have 4 of them because I have a 4 here in the complex, and then I'm going to form this. And then I noted over here what the Kf was, but it's given here, so that's optional to write down. But I went ahead and made an ice table here, and trick number 1, for my initial concentration of Hg2 plus, it gives me this number here. But what we have to take note of is that we have equal volumes of both of these, and once we mix them, this molarity is going to be less than what this number is. Say we had 1 liter of HgNO3 added with 1 liter of NH3. Our final volume now is 2 liters. So to get the molarity, you have to divide it by 2. So you can divide this number by 2 every single time and use those values and it will work. Once you do that, you can put those numbers into your ice table. So I have my 0.0029 for my Hg2 plus and my 0.05 for my NH3. And then I just did everything like you would do a regular ice table. Minus x minus 4x, because I have a 4 as the coefficient, and plus x. But here we run into a problem. We can't use the small x approximation here, because if I get rid of this x in this term, I'm not going to be able to find my Hg2 plus concentration easily. And that's what the problem is asking for. So there's a better way to do this. We know that Kf is this super big number. 10 to the 19 is giant. And because it's so big, we can assume that the reaction goes to the right. So it goes to completion. And because of this, we're going to go ahead, send it to completion. Now we're going to do an ice table for the reverse reaction. That way we can find the equilibrium molarity. So I just wrote out the exact same expression down here, rewrote my ice table, but I'm going to change up the values here. For Hg2 plus, since the reaction has already occurred, we're going to assume that all of this has been used to form the complex. So whatever number I had here for my initial concentration, I'm going to pop that right over here for the complex ion, and I'm going to put 0 for my Hg2 plus. Now, here's another trick with this problem. We have a limiting reactant here. Because we have 1 Hg2 plus versus 4 NH3s, the number that I put here needs to take these details into account. Now, luckily, it's not too difficult to calculate this number. All you have to do is take this 0.0029, or whatever number you have here, and multiply it by the coefficient here. And I have it written out over here. Once you get that number, you're going to subtract it from the number that you have here. So I did my 0.0029 times 4, that gave me 0.0116. Then I did the 0.05 minus the 0.0116, and that gave me the 0.0384, and that's what I'm going to put into my ice table. Now, once I have all of these values here, usually I would do minus x, minus 4x, but because we're in reverse, we're doing plus on the reactant side and minus on the product side. Because we're going this way, the minus side is over here because this is where we started, and all this stuff is going to be moving over here. So I do plus x, plus 4x, minus 1x. And when I do this, I'm going to have x, and then I'm going to have this and this. Here we can use our small x approximation. Because this x value, this concentration of the Hg2+, is going to be so small compared to our Kf value, we can basically ignore it. That's one of the rules. We can do that. So we're going to do that because it simplifies the math so much and makes this problem so much easier. And I'm sure that you've already used that in earlier ALEKS problems that you've had to complete in order to even get to this problem. So once we do that, and we set up our actual expressions here, we just need to solve for x, and that's just algebra. There's multiple ways for you to do it. What I did is I just multiplied this out, so I did 0.0384 to the 4th, and then that gave me this number. And then I kept the x on there. I just multiplied it out on both sides so that it canceled these. Then I multiplied these two together, and that gave me this number. And then to solve for x, I just divided by that 4.15 times 10 to the 3. And that gave me this number here. And to 2 sig figs, it's 7.0 times 10 to the negative 17th molar. And I just put that right in here. And so you can see it's not really that terrible of a problem if you have the framework going into it. I think if you try and go into this problem without any explanation, it can be really frustrating to figure it out. So I hope that helps and makes this problem a lot easier for you. I know that it did for me, and I have a couple more examples here to show you. The only difference between these ones is that this is NH3 and then this is NaCN. So this will split apart into Na plus and Cn minus. But you just use the Cn minus. You can just ignore the sodium. That will just be a spectator ion. Same thing with the NO3. Everything else about this is the exact same. I won't go through these just for the sake of time of the video, but feel free to pause and compare what you have to these two examples. And yeah, I hope that helps, and good luck.